Here we want to calculate the following surface integral, and S is the outer face of the pyramid, which is delimited by the following surfaces. Let me write them down. One is the plane x plus y plus z equal to a. Another one is x equal to 0. Another one is the plane y equal to 0, and the other one is z equal to 0. Let me also tell you that the integrand here can be written in another fashion, more concisely like this. We have the vector x, y, z. We have to take the dot product with the normal to the surface ds, or sometimes we can also rewrite nds as the vector ds. And the vector ds is characterized by three components, which are three surfaces, and we can write it as dy dz, which is the surface normal to the x-axis. Then we have dx dz, the surface that's normal to the y-axis, and then we have dx dy. Now let me sketch the surface that we have to integrate over. Here we have the z-axis, then let me draw the x-axis like this, and then somewhere here we have the y-axis. And if we consider this plane, and also the fact that we have to consider the planes x equal to 0, y equal to 0, and z equal to 0, we have the following surface. It's a pyramid. It is something like this, where this portion of the surface here is the one that's given by that plane. It's a portion of that plane, and then this length here is equal to a, then this length here is equal to a, and this height of the pyramid is equal to a. It's easy to see from this equation because, for example, if you want to find this length in red here, well, you have to set x and y equal to 0 here, because of course they are equal to 0 along the z-axis, and then you will get z equal to a. So this point here is located at a height equal to a with respect to the origin. Something similar for this one and this one here. So we have to integrate over this pyramid, the surface of the pyramid, not the volume, just the surfaces. And we have 4 surfaces, right? So if we consider, for example, the surface located on the xy plane, this one in blue here, then we know that the normal to the surface is k. It is directed along z. So we can rewrite this integral as a sum of 4 integrals. I will just use an integral sign here, and we have to integrate over the plane z equal to 0. Not the overall plane, only this portion of the surface. But for the sake of simplicity, I'm just going to write integrate over z equal to 0. It is not the whole xy plane, because z equal to 0 is the xy plane. So this is the xy plane. If we take the dot product between this vector and this vector here, we are only interested in the z component, because the normal to this surface is equal to k. So we have z times this component, dx dy. So we have to integrate over dx dy over that surface. And that's quite intuitive, because we are integrating on the xy plane. Then something similar for the plane x equal to 0, which is the yz plane. And then we have to integrate x, the first component, times dy dz, because we are integrating over the yz plane, so the only contribution here is given by this first component and this first component here. When we take the dot product, we only have that one. Then we also have another contribution here given by the plane y equal to 0, so we have to integrate over y equal to 0, which is the zx plane. Of course, in this case, we only have the contribution given by the second component y times dx dz, or dz dx. And finally, we have to integrate over this plane here, which is this region here. And in that case, we have to be more general So I will rewrite the integral like this. We have to integrate over the plane x plus y plus z equal to a, and then we have the vector x, y, z dotted with n ds. And as we will see, these integrals will simplify a lot, because, for example, when we integrate the first integral over z equal to 0, this term will be equal to 0. So this will give a 0 contribution. But also the second one, because we have to integrate over x equal to 0, and here's x. So this will also be equal to 0, and so will this one. So we only have to consider this contribution here. And we have to remember how to write down, how to integrate surface integrals. In particular, we know that n ds can also be written like this. So if we have, for example, some surface, and we want to consider this point, which is a vector x, that we describe with respect to some origin O, for example, and in order to parameterize the surface, we need two parameters. So these parameters can be u and v. So for example, when we take the derivative with respect to u, we are going to move in this direction, and then we are going to get this direction, for example, if we take the derivative with respect to v. So if we consider the cross product between these two vectors, we are going to get the infinitesimal element of the surface. So we are going to get the surface element, and not just the surface element, but also the normal, and ds, because if we take the cross product, we get a unit vector that's normal to the surface. So nds will be equal to the cross product between the derivative of x with respect to u and the derivative of x with respect to v, and then we have to multiply by du dv. In our case, we can write down the vector x as given by three components. In Cartesian coordinates it is just x, y, z, and z is a function of x and y, so we can rewrite it as f of xy. I want to do it like this. So dx du is equal to dx over dx. So please do not get confused between this x here and this vector x. They are different. And this is equal to the vector 1, 0, f sub x, where f sub x is just the partial derivative of f with respect to x. And something similar for dx dv. This will just be given by dx dy, and therefore we get 0, 1, f sub y. So the cross product will be given by the determinant of this matrix, I, j, k. Then I will put 1, 0, fx, 0, 1, f sub y, and then this will give me, the first component will be minus f sub x, then I have minus f sub y, and then I have 1. Now I can use this result in the integral that I want to calculate. This will be equal to integral, if I take the dot product between this vector and this vector here, which is just minus fx minus fy, 1 times dx dy. Dx dy are just du dv. I have chosen u equal to x and v equal to y. So this will be minus x fx minus y fy plus z times 1, but z is just f. It is the function f of xy, and then I have dx dy, and also remember that I have to integrate over the portion of the plane which is given by the equation x plus y plus z equal to a, where z is the function f of xy. So if we consider this function, f is just a minus x minus y. So if I take the derivative with respect to x, I will get minus 1, and also if I take the derivative with respect to y, I will get minus 1. So this will be given by integral x plus y, and then I have plus f, which is plus a minus x minus y dx dy and this gives me a times the integral over dx dy, and now I have considered the projection of the surface on the xy plane. So now what I have to consider is just the projection of the slanted portion of the surface on the xy plane. So let me do it in blue here, this one. So this curve in particular is just given by the equation of the plane where I set z equal to 0. So this is just equal to x plus y equal to a. So if I take a look at that from above, I see something like this, xy, then here I have the line x plus y equal to a, and I have to integrate over this area. And it is a double integral, so it's quite simple. So what I have is the following. This constant a, then I have integral, then I can integrate first over y, for example. So when I move along the y-axis, I am going from 0 to this equation, the equation of this line, which is y equal to a minus x. And also remember that the length of this portion is equal to a, and also the length of this portion here is equal to a. So I have to integrate from 0 to a, then from 0 to a minus x dy dx. And this is just equal to a integral from 0 to a of a minus x dx, but this is just equal to a times a squared minus a squared over 2, and this just gives me a cubed over 2. And this is the result.